Okay, so in this chapter we'll be dealing with nuclear chemistry. And as the name suggests, this area is dealing with the changes that takes place in the nucleus of an atom. So this is different from what we were discussing in terms of chemical reactions and so on, because in the case of chemical reactions, we have changes in the number of electrons around the atom, especially the valence electrons. That is not the case in nuclear reactions. In nuclear reactions, there are changes in the nucleus. And as such, there are some fundamental differences between nuclear reactions and chemical reactions. But before we get into that, we need to review some definitions that you should have been exposed to at least in introductory chemistry and also in general chemistry. So you should be familiar with the concept of atomic number, which is simply the number of protons in the nucleus of an atom. And the mass number of an element is the sum of the number of protons and neutrons in the atom. So the symbol Z is basically the symbol that is universal for representing a number of protons, and A is the symbol for representing the mass number. All right, so the isotopic symbol, I'm quite sure you're all familiar with this, where we write the symbol for the element represented by the X here. Up here as a superscript, we have the mass number, and down here we have the atomic number. All right, so X is the element symbol, A is the mass number, and Z is the atomic number. All right, so just some examples here. A proton can be represented by either this or this, but in either case you have one as the mass number and one as the atomic number, right? So A is equal to 1, Z is equal to 1 for the proton. The neutron is another fundamental particle, and as you can see here, it has a mass of 1, and you see here that it's designated an atomic number of 0, all right? And that's primarily because it has no charge, right? Then the next fundamental particle is the electron. Now, in the nuclear science or nuclear chemistry, we refer to the electron also as a beta particle, right? And in the case of the electron, as you can see, the mass number is 0 and the atomic number is -1. So you can use this representation here with the E, or you can use beta, the Greek letter, to replace the E, but the numbers are still the same. So in that case, the atomic number is 0 and the mass number is the mass number is 0 and the atomic number is -1. And then there's another particle we're going to talk about later on, which is known as a positron, which is seen as basically the opposite of the electron in that its atomic number is +1. So it has a charge of +1 but no mass like the electron. So you can use this representation or you can use that representation as well. All right. And lastly, another fundamental particle is the alpha particle. The alpha particle is basically the helium-4 nucleus. So this is the symbol here, where the mass number is 4 and the atomic number is 2. You can also use this symbol where the He is replaced with the Greek letter alpha, and so that's another fundamental particle. So these are the fundamental particles we'll be dealing with. There are some others, but at this level, these are the ones that we're sticking to. Now let's talk about nuclear equations, and in fact, we're going to talk about how do we balance nuclear equations. And here you're going to see some differences, all right? Because a couple of things you have to conserve when it comes to balancing the nuclear equations. One thing you have to conserve is the mass number, right? So the total mass number on the left side for all the reactants must be equal to the total mass number on the right side, all right? Another thing, well, before we get into the other rule, let's look at this example. If you look at this example here and look at the mass number total on the left side, 235 plus 1, that's 236. If you look on the right side, you'll see that the 138 plus 96 plus 2 times 1 will give you 236 as well. All right? So that's basically one rule that must be satisfied when balancing nuclear reactions, right? So as shown there, 235 plus 1 is equal to the sum of the mass numbers on the right side. Another thing that must be conserved must be the atomic number, right? Total number of protons on the left side must be equal to the total number of protons on the right side. Or in fact, more specifically, nuclear charges, all right, must be conserved. So going back to this example, if you count up 92 plus 0, that gives you a total of 92 on the left side. And if you add up 55 plus 37 plus 0, well, 2 times 0, you're going to get 92 as well, all right? So those are the things that must be conserved when it comes to nuclear equations. So for example, let's say you're given this question and it says polonium-212 decays by alpha emission. Write a balanced equation, nuclear equation for the decay of polonium-212. All right, so the alpha particle, of course, you should know, is, as I said before, the helium nucleus. So it decays, right? That is, this particular isotope decays, which means that it produces alpha particle, and then it produces, of course, another particular nucleus, which it has to in order for the mass numbers and the atomic numbers to be conserved. So therefore, to find the mass number for the element X, in other words, to find A, we know that A plus 4 must be equal to 212, right? So therefore, by simple arithmetic, we can determine that A is equal to 208. As far as Z is concerned, the atomic number for the element X, we know that Z plus 2 must be equal to 84. So again, by simple arithmetic, we can determine that Z is equal to 82. Now, the next question is, what's the identity of the element? And that's simple, because remember, each element has its own unique atomic number, so therefore all you have to do is consult the periodic table and see what element has atomic number 82, and you'll see that that element will be lead, and therefore this would be the product X, where the mass number is 208, the atomic number is 82, and the symbol would be Pb, which is a symbol for lead, and therefore this will be, as a result, the balanced nuclear equation for the decay of polonium-212, all right? So that's basically how you do that. Okay, now this is a side-by-side comparison of chemical reactions and nuclear reactions, and I made mention of the fact that there are fundamental differences between the two. The first one listed here is that in the case of chemical reactions, what you have are the rearrangement of atoms and the breaking and forming of chemical bonds. All right, that's what happens in a chemical reaction. However, in a nuclear reaction, what you have are situations where you have elements or isotopes of the same elements being converted from one to another, right? So basically, what you have in the case of nuclear reactions is basically one element being converted into another, or you can have one isotope of an element being converted into a different isotope of the same element. So that's one difference between the two. The second difference is that electrons in the atomic or molecular orbitals are involved in the forming and breaking of bonds, right? Only electrons are involved. The nuclear particles are not involved in chemical reactions. But over here, protons, neutrons, electrons, and other elementary particles may be involved in nuclear reactions, all right? So that's another important difference. The third difference is that in terms of the amount of energy that is absorbed or released in chemical reactions, the amount of energy is relatively small compared to nuclear reactions. In the case of nuclear reactions, they're typically accompanied by a tremendous amount of heat loss or heat absorption, all right? And then the fourth and final difference between the two is that the rates of chemical reactions, as we learned when we talked about kinetics, we learned that the rates of chemical reactions are influenced by these different factors: temperature, pressure, concentration, and the presence of a catalyst. In the case of nuclear reactions, they are not affected by any of those factors, all right? So if you increase the temperature or decrease the temperature, or if you add a catalyst or change the pressure, you're not going to affect the rate of nuclear reactions. So that's basically the difference between, or the differences between a nuclear reaction and chemical reactions. Okay, now what we're going to do here is look at the different types of radioactive decay that can occur, and we can see where the result of these decays will produce a nuclei or a nucleus which is stable. So the first type of decay we're going to look at is the beta decay, and one example is shown here where carbon-14 which is shown over here, becomes converted to nitrogen-14, and you'll see here that there's a beta particle that is produced, as well as some energy being produced. So when you see the symbol, it means basically that energy is produced. Here's another example. Again, in this case, potassium releases a beta particle along with some energy, and the nucleus that is produced is calcium. All right? Now, what these changes have in common is that there is an increase in the atomic number by a unit of 1. All right? In the case of the first example, the atomic number of carbon is 6, but it increases to 7 when a beta particle is lost. The same is true in the case of potassium. Its atomic number is 19, but it increases by 1 to 20 when calcium is formed as a result of a loss of a beta particle. And the reason why that happens is that in the nucleus, what happens is a neutron is converted to a proton and a beta particle. So the result of that is that, as you can see here, the proton remains in the nucleus, and as a result, the mass of the nucleus increases by 1. All right, while the mass number, I should say the atomic number increases by 1, but the mass number remains the same. All right, so this is the actual change that takes place when a beta particle is produced. A neutron is basically converted to a proton and the beta particle. The beta particle is emitted and the proton remains in the nucleus, right? So as stated here, the change is basically that the number of neutrons is decreased by 1, but the number of protons is increased by 1 as well. So basically there's no net change of the mass number, but there will be an increase in the atomic number by 1. All right? Okay, the next type of decay we're going to look at is what is known as the positron decay. And as we said before, the positron is basically the opposite of a beta particle. So as we can see in this example, carbon-11 undergoes a positron decay, some energy is produced, and you're going to end up with a new element, which is boron-11. And so that's one example. Another example is in the case of potassium-38, when it undergoes a beta decay, it produces argon-38. In both cases, what you'll observe is that the atomic number decreases by 1, right? So for the first one, there's a decrease by 1 from 6 to 5 in the atomic number, and in the case of potassium, there's a decrease by 1 from 19 to 18. And the reason why that happens is shown right here. What happens is that a proton is being converted to a neutron and a beta particle. So as a result, when you look at the change in the atomic number, it decreases from 1 to 0, and as far as the mass number, it stays the same, and that's basically the reason why. The beta particle will leave and the neutron will remain in the nucleus. So as stated here, there will be an increase in the number of neutrons and a decrease in the number of protons by 1. Okay, so and another thing here that is mentioned is that as far as the energy that is produced is concerned, which is usually in the form of some type of radiation, they will have no mass number or atomic number. So therefore, you don't take those into consideration when you're balancing nuclear reactions or nuclear equations. Okay, so let's look at the next type of decay called electron capture decay. So it's not really a decay because you don't have something breaking up, but the principles still apply. So this is the first example, this is the second example. In both cases, what you'll notice is that the atomic number is reduced while the mass number remains the same, right? Now, the reason why that happens is because in electron capture, what happens is that the proton in the nucleus will combine with an electron to form a neutron according to this equation, all right? So what happens as a result is that the number of neutrons increases by 1, and the number of protons decrease by 1. So therefore, the net result is that the mass number doesn't change, but the number of protons decrease. So from 18 to 17 in the first example, and from 26 to 25 in the second example. And then we get to alpha decay. And we remember that the alpha particle is the helium nucleus, and the result of an alpha decay is that the number of neutrons will decrease by 2, and the number of protons will also decrease by 2. And this is basically what happens in alpha decay, all right? And then you can have spontaneous fission, where you have one heavy nucleus being broken up into more than one nuclei, and other particles may be produced, as you can see in this example, where californium is spontaneously breaking up into indium, actually 2 indium nuclei as well as 2 neutrons. Now, how do we predict whether or not a type of emission will take place or a type of decay will take place? Well, what you see here is a plot of different isotopes. On the y-axis, you have the number of neutrons, and on the x-axis, you have the number of protons. Now, this line here is a line where the number of protons will be equal to the number of neutrons, right? And then when you plot the stable nuclei in terms of the number of protons and neutrons on this graph, what you'll find is that those stable nuclei will lie along this belt of stability, right? Now, what you'll find is that there are other particles which are not as stable, which would lie in this region above the belt or in this region below the belt. And as you can see here, you can predict the type of emission that will take place when you have nuclei here or here. If you have nuclei above the belt, then it says here that those nuclei will undergo spontaneous beta emission to produce a nuclei that will fall closer to the belt of stability. On the other hand, if you have particles below the belt, then basically what will happen is that those nuclei will undergo positron emission or electron capture, and the resulting nuclei will have a neutron to proton ratio which falls closer to the belt. So the point here is that nuclei which falls outside the belt will undergo certain changes so as to produce products which fall closer to the belt. All right. So if the nuclei falls outside here, that means that the neutron to proton ratio is too large, and beta decay would be the most likely emission that will take place so as to produce a particle which falls closer to the belt of stability. On the other hand, if you have particles on this side where the neutron to proton ratio is too small, then either positron decay or electron capture will occur so as to produce a new particle which falls closer or falls within the belt of stability. All right. Now, it turns out when we examine the stability of certain nuclei that there are certain numbers of neutrons and protons that would have to be present in order for the nuclei to be extra stable, right? So basically, if the number of protons or neutrons are equal to these numbers here, we call them magic numbers, then you'll find that the nucleus, which has these numbers for protons and neutrons, will tend to be more stable, right? And it's kind of similar to certain numbers associated with stable atoms or stable ions when it comes to the number of electrons, 2, 10, 18, 36, and so on. So that's one thing that is observed. Another thing that is observed is that nuclei with even numbers of protons and neutrons, they tend to be more stable than those with odd numbers of protons and neutrons, all right? And then here is the final point here in terms of nuclear stability. All isotopes of the elements with atomic numbers higher than 83 are unstable and therefore reactive, all right? So those are just some rules which you can use to predict whether or not a nucleus is stable, all right? And down here is a table which gives you the number of stable isotopes with even and odd numbers of protons and neutrons. So in this particular case, the nuclei with odd number of protons and odd number of neutrons, there are only 4 of them. If you have a nuclei with odd number of protons and even number of neutrons, there are 50 of them. And then here, if you have nuclei with even numbers of protons and odd numbers of neutrons, there are 53 that fits that bill. And then here, if you have nuclei with even numbers of protons and neutrons, there's 164 of such stable isotopes. All right. Okay. So, oh, and another point here being made that these two particular elements, all their isotopes are radioactive. Okay. Now, how do we measure the stability of these isotopes? Well, there's a thing called the nuclear binding energy, and by definition, this is the energy required to break up a nucleus into its component protons and neutrons. So, in other words, let's say, for example, we're focused on the fluorine isotope here, fluorine 19 isotope. It contains 9 protons and 10 neutrons. So therefore, to break this up to form the separate particles, the energy required for that would be the binding energy. Now, one thing you need to remember, and this is very important, and this is one big difference between nuclear reactions and chemical reactions. In the case of chemical reactions, the conservation of mass rule or law applies. If you remember, the conservation of mass law basically says that in a chemical process or a physical process, the total mass is conserved. In other words, the mass of the products will be equal to the mass of the reactants. Now, that is not true for nuclear reaction, because what you're going to find is that there's a difference between the total mass of the products in a nuclear reaction and the total mass of the reactants. And this is also true in a situation where you're looking at a reaction where a nucleus is being broken up into its separate particles, right? And the difference between the mass of the particles and the mass of the original nucleus, we call that the mass defect, all right? So we can use the mass defect to determine the binding energy by using this formula, right? Where E is the energy, and that will be equal to delta M. Delta M is the mass defect times C squared, where C is the speed of light, which is equal to 3.00 times 10 to the 8 meters per second. So we can calculate the binding energy by finding the mass defect first. So that is what is being done here. The binding energy, well, actually this equation here, even though they have the binding energy here, is actually the mass defect being calculated here. So 9 times the mass of the protons plus 10 times the mass of the neutrons, right? You add that up and you subtract from that the mass of the nucleus of fluorine 19 itself. These are all measured in AMU units. So when you put those numbers in for the mass of the protons, neutrons, and the nucleus of fluorine 19, as you can see here, this works out to be equal to 0.0 or 0.1587 AMU. That is the mass defect, which if you put this into this equation here, delta M, you're going to get your energy. So based on this relationship, 1 AMU is equal to 1.49 times 10 to the minus 10. So basically what that means is that if you put 1 AMU here, multiplied by C squared, you're going to get this amount of energy. So you can use this as a conversion factor. So when you use this as a conversion factor to multiply this mass defect here, you're going to get 2.37 times 10 to the minus 11 joules, all right? So that's the binding energy. Now, the binding energy in and of itself is not the actual measure of the stability of a nucleus. What you'd have to do is take the binding energy and divide it by the total number of nuclear particles, or otherwise known as nucleons, right? So when you take the binding energy and divide it by the number of nucleons, then that is what we use as a measure of the stability of a nucleus. And what we find when we do certain plots, well, let's do that for this particular particle. So the binding energy is 2.37 times 10 to the minus 11, and you divide it by 19, which is the total number of particles, protons, and neutrons, and you're going to get your binding energy per nucleon being equal to 1.25 times 10 to the minus 12 joules per nucleon, all right? So when we do a plot of nuclear binding energy per nucleon versus the mass number, this is what we see here in terms of the energy required to break up the different nuclei on this level, on this basis, the binding energy per nucleon, right? So basically these are the stable particles, like the iron 56 nucleus, or the helium 4 is not far from there. uranium-238, and so on and so forth. All right. So what you see here is that as the binding energy per nucleon increases, the nuclear stability increases. Okay, let me just show you this particular graph. Or not graph, but a flow chart, so to speak. It's basically showing you a series of nuclear reactions where you have different decays at each stage. This one is mapped out, which shows from the beginning, you start off with uranium-238, and it produces thorium-234, and it goes on, and it can take actually different pathways, as you can see here. And the final product of this whole process would be lead-206, all right? Now, in between each of these arrows, you'll notice that there are some numbers here which gives you some measure of time. 4.51 times 10 to the 9 years, 24.1 days, 1.17 minutes, and so on. These are the half-lives of these reactions, right? And we learned about half-lives when we were talking about chemical reactions, when we were discussing kinetics. You're going to see this term come up again when it comes to nuclear reactions in this chapter, all right? In fact, that's what we're going to discuss in the next video. Okay, so we're going to stop here for now.